Hi and welcome to week 8 of Maya Bifrost training. This week we're going to be looking at doing this lovely martini glass water simulation and just get back to the basics of simulating, meshing and rendering Bifrost liquids and how to get really nice results for sort of like TV commercial advertisements, wine commercials or other things like that you might use in a sort of small studio environment. And we're going to be having a look at the shader for the glass and the water. And we're just going to be doing a basic setup with this scene so that it's easy to use and you're able to get some pretty good results. So I've got two files here. One is world scale glass. And what we're going to do is just cover some of the issues you might face with incorrectly scaled collision or emitted geometry. So what this glass actually is it's the correct geometry, but it's actually scaled to be microscopically small, which may be the size of the asset in your TV commercial shot. So one of the problems with effects is you really need to have the voxel size or the fluid Maya fluids voxel size or the real flow size be correctly set for the actual simulation to work nicely. And so what I've got here is you can see I've had to set the voxel size to 0.001. So that is a hundredths of the size of the regular size for Bifrost fluids, but that's the size that I've had to set this emitter object to actually generate dense particles inside this glass. And basically what the problem is that when the voxel size is set that small, it's not only the voxel size that you have to set to be tiny, it's also the sub-steps that you have to increase massively, and you have to change basically a whole lot of settings. And then even once you change them, because of its microscopic size, the simulation will be very unstable, and it can even crash the software as you're simulating it. And the reason for this is because on an actual on the scale of what the fluid solver is working at, this would probably be about the size of a pinhead, and it's comfortably simulating sort of 6 foot long beach kind of waves, and we're trying to crank this tiny little pinhead water simulation into the naturally working and correctly simulating kind of big beach simulation. And all it's going to do is it's going to fail to compute correctly the results, and no matter how much of settings and effects that you change at this extremely small setting, you're going to run into problems. Now this is an extreme result. You'll obviously get it to work eventually if you change the settings around enough, but basically what happens is you'll get errors in the simulation if it's too small or too big. So what not only will you get errors, but you also get instability in the program. So in RealFlow or Bifrost, if you've got a really massive or really small collision or object that you're using for your simulations, you'll eventually crash. You'll eventually crash Maya, or you'll crash RealFlow. So this is a pretty common beginner mistake with using water simulation software. So the trick is to actually get your emitter or collision geometry and actually scale it up to the size that that works. You already know works. So in Bifrost, we can see a working example they've set up, which is this milk pour scene. So we're not going to actually use this through our simulation, but you can see that the scale of the demo scene that the developer has made has is much larger than my my real world scale cup that I've put into the scene. So you can see here, obviously, why the simulation is crashing the software and not working, because the demo one is almost 100 or 1,000 times larger than the microscopic one that looks like something out of Honey, I Shrunk the Kids. So basically what you do is you scale up the scene that you're using, and that'll enable you to get working results as the software has been designed for. Now, this obviously has a bit of leeway, but not much, because which I'll explain shortly. So the demo on the right hand side is a glass of milk being poured, and the TD that's actually programmed the Naiad software themselves has got it to work so it looks like a glass of milk being poured. If I was to make this martini glass this high, what it would actually look like is it would look like an ocean of water being poured into the martini. There would be so much turbulent detail that it would look way, way, way out of scale. Now, without trying that out to start with, you wouldn't know, but it would take, maybe 7 or 10 or 20 minutes per frame to simulate, and the resulting simulation mesh that you would generate would look more like a swimming pool than a martini glass. So the scale is very, very important for water and fluid simulations to get correct. So that's one of the main reasons why it's very important to set your scene scale so that you have enough detail and you have not too large and too slow simulation time. So you want to get a good trade-off of like making it not look blobby and look like porridge pouring into it, but also making it look like it's right. So this is the glass fluid scale scene, and we're going to make from scratch a fluid that's going to be pouring into this collision object. So what you can do is, now that the scale is correct of the scene that we're working with, we're just going to create a cylinder, which is going to be the emitter object for this scene. So a couple of people on the forums were asking, oh, well, how can you set the settings for, really big or really small simulations? Well, the key thing is with water simulations is the scale is really based on the solver itself. So the Navier-Stokes solver works at a certain sort of optimum scale, and the Bifrost simulator works at its optimum scale as well. And it's really the scene that you need to scale, not the Bifrost simulation. But the advantage of that is that if you make one scene like the helicopter crashing into the beach or something else, what you can actually do is you can reuse that same simulation settings once you've perfected them and got a really, really nice looking water and a really, really nice shader. You can basically import any kind of collision geometry, be it dinosaurs or speedboats or ships or logos or pouring liquids or anything like that, and you'll actually know the exact results that you're going to get from that simulation without having to go through labor-intensive revisions to what you're doing. So that's the real advantage of the software, is that it creates results which you can anticipate and work really well. So that's one of the great advantages to keeping the same settings on the fluid solver and adjusting the scale of your scene. So what I'm going to do here is just going to put the master voxel size down to 0.02, and what this will actually do is it will emit water particles or liquid particles out of this cylinder. So one of the ways you can do pouring is to accelerate the liquid out of a cylinder using a certain directional velocity, so you can accelerate it across the x-axis or the y-axis. But one way that I like to pour liquids is to create a flow object. And what a flow object is rather than the particles just falling straight down out of the geometric emitter, you can actually pour the liquids into the flow objects, and that will flow down the object and then into the container that you're using, and it'll make a much more realistic liquid geometry coming out of the flow object than it does if you just emit it from like a circle or a box. So how you make this flow object is you basically model with polygons the end of a pouring container, like a juice container or a cocktail container or a coffee container or a wine bottle. And all you have to do is basically create a kind of trough with an opening at one end, and then that will actually allow you to pour the liquid particles in one side of it, and then have it pour out the other side. So it doesn't need to be too high polygon, the container, but all you really want to do is just have an interesting shape that you can flow the liquid down that can make a nice like a nice geometry when it comes out the other side. So that's one of the main things that's really good for pouring liquids. So what we've done here is just made a simple polygon box, and just going into the lattice deformer, which is in animation menu, and you just want to make sure that you're not creating one with 50 points or with not enough points. You need to really have at least 3 or 4 divisions to get it working properly. And once that's made, you'll be able to create that and then select the lattice points as opposed to the vertices. And you'll be able to bend that around and just create a bit of a, like a funneling shape. It's not really important how it works, but you just don't want to get the liquid to kind of spray off it in a weird way. You just want to make it kind of flow out in a fairly make sense, kind of way that would be the way it would work on a real container. So once you're done, you just position the flow geometry where the liquid is, and then you can simulate the geometry and see how the liquid comes out of it. So one of the things is you might make this epic piece of flow geometry, and then the water looks really bad as it comes out, like it might spill over the sides or do all kinds of really nasty things that you're not keen on. Don't worry too much about this. That just might be because your emission is too high, or because your flow object's too small or too big, or it's positioned incorrectly. So it's a good idea to just use trial and error as you're positioning and moving it. And ultimately what you want to do is emit a lot of particles into it, pour the fluid out of the container into the glass or into the logo that you're using. And then what you'll be able to do is animate both the emitter position and the flow geometry position. Now what that'll actually allow you to do is it'll give a very natural kind of like pouring motion into the glass, so that you'll be able to get the right natural sort of flowing results. And what you're trying to avoid is that kind of like computer generated circles, squares, and these very unnatural shapes sort of shooting water out of them. I mean, water is a very organic flowing substance, and it doesn't really line up with those kind of geometric shapes. Even out of a hose, it's immediately a very dynamic shape straight out of the nozzle. So just try and break it up as much as you can as it's sort of flowing down the object, and in that way you'll be able to get the best result for the pouring liquid. So as you can see at the back here, we've got a few particles spilling through the back of the geometry, and we're going to address that to begin with a kill plane. So what happens is the kill plane will actually delete those particles at the back as they intersect with it, and that'll allow the calculation to not have to keep them in memory as it's doing the sim. Some of the particles that fall down or go off to the sides of the simulation can greatly increase the voxel size and the simulation time of simulations, which is really unnecessary. So whenever possible, using when you're doing fluid sims, it's a good idea to make kill planes to eliminate any of the particles that are not necessary for the actual pouring or waterfall or boat or whatever simulation that you're doing. It's really important to just keep your simulations in the most fixed sort of area possible. So in this sim, you can see there's water pouring off at the start, right down the back of the collision geometry, and that's actually falling way off the scene and causing a lot of extra simulation time to be incurred. And the other thing too is, if it's actually forwards enough, you'll actually be able to see it in the render, and that's definitely something that you don't want to have to deal with. Is meshing particles that are just part of the emitter object. So what we're going to do here is create a kill plane, and then we're going to position it right where that splash is. So we've just flushed the cache. Going to decrease the size of that emitter a little bit, and then we're going to rotate this collision object, position it so that there's less overflow of that emitter, and then we're going to make a kill plane and just position that just under where the water is. The other thing we might do is position this emitter closer to the tip of the flow object, and what that'll do is it'll mean that the fluid has less sort of horizontal distance to carry, and less sort of errors are going to happen, and less sort of flow coming out the back of that geometry. So with kill planes, you can create them from mya218, but they also just create themselves as these little boxes. And once you've made one, you can scale it and rotate it where you need to go, and that will allow you to kill all the particles that are in that incorrect area of the scene. One thing to be cautious of though is some of the kill planes have infinite extents, and what that means is that the limit of the kill plane goes beyond the edges of that little green box. So every single particle that hits that plane to infinity will be deleted. So you just have to be cautious that you're not actually deleting particles that are getting emitted into the X or Y coordinates of that kill plane. So we can see here that that kill plane is actually deleting the particles flowing off the edge of the collision object. So what we're going to do is just reposition that kill plane to be a little bit more off the particle path, and then we'll be able to simulate the liquid pouring down the flow object into the cup, and then we'll see how the particle settings are working for actually filling up that martini glass. So sometimes your emitter can be too strong, and what I found in previous simulations is if the emitter is too large or its emission rate is too high, the glasses or the cups or whatever will fill up too quickly and overflow and look really silly. The other thing that can happen is if your glass is scaled too small, the liquid will fill up too quickly and overflow, and if it's too big, it'll fill up too slowly, and it'll look a bit boring because it'll take like 50 seconds to fill up. So it's important that you get enough particles, a small enough emitter, and you have your martini or wine bottle or whatever set at the right scale to get the pouring effect that you're after. And if you get all these things set up correctly, you should be able to fill up the container that you're working with in a very natural amount of seconds, the same as you would actually pour a real glass of water or alcohol into a container. And that's really good indicator if it's doing the thing that you want. And I'm sure in future versions of Bifrost, they're going to have more controls to actually adjust the particle parameters. So one of the really good things about photoreal liquid simulations is you can actually defy physics. So rather than just making a TV commercial and say, oh, we just got this martini pouring into the cup, you can actually have, multiple glasses, multiple directions of gravity, forces affecting the water to do physics-defying flowing patterns, but it still behaves like natural water, but more like in space or with multiple directions of gravity and all kinds of really interesting effects. The other thing you can do is flick water out of a container and have it form into a logo or an eagle or the brand of the wine or whatever it's doing, using attractor geometry. So RealFlow has this as one of its features through different scripting and things like that. But no doubt Bifrost will also have this feature down the track where you can actually attract the particles from a splash into a shape. The other way you can cheat this is by having hollow geometry and actually pouring the water into the hollow geometry to sort of fill it up, and it will actually fill up like the model of a woman or a bird or any kind of like geometry that you model that it can flow into. So that's another way you can do this sort of TVC small scale water and get it looking really nice. But your end results are always going to be a result of the simulation that you've run, how detailed it is and how stable. I wouldn't be running dodgy sims and then expecting the meshing to save the day at the end of it, because really the simulation and the particle position and their stability and their look is going to drive the look of the water at the end of the day. So if you've got dodgy looking simulations happening that aren't working, you're definitely going to get a dodgy looking render, no matter what kind of shader or what kind of detailed meshing you put on the liquid. So I'm just repositioning this pouring geo, and once you're happy with the results, you can basically animate the emitter and the pouring geometry, and then give it a kind of like a bit of a sort of movement forwards and backwards, and then that will actually look pretty good once you've animated that to pour in a lifelike way. And then to turn the animation off, all you have to do is select the emitter geometry, which is the P cylinder, and set a keyframe on its enable on or off button. And what that will do is it will just turn off that emitter at that certain frame. The other way you can turn off emitters is if you keyframe the continuous emission on button, and that'll set it as well. One other thing to notice is with small detailed scenes like this, you can sometimes increase the simulation substeps. So we're just opening now this martini pour 4.myascii. Now this has actually got a slightly different simulation. It's just using the emitter geometry of that cylinder and the glass, and I've animated the some keyframes on the position of the emitter, and then the particles are pre-set up to work really nicely on this scene, so that you can see how it looks and test it out, because this is the scene I'm going to use to render this this liquid and mesh. So you can see here I've set some keyframes on that emitter. Now the keyframes make a big difference to the simulation. They really give the water like a natural movement as it's filling up the glass, and it's really important to get your keyframes so they don't look really silly or like too fast or too slow or stuff like that. So just use that to the best of your ability, and set the keyframes like so, and then you'll be able to get a nice kind of liquid movement. Now, what I was saying before about the substeps, the substeps is basically the accuracy of the simulation, which makes it slower or faster. So this simulation works pretty good with substeps of 3000 max substeps. The min substeps will be 1. So the main thing is to get it working really nicely, you want to have settings that aren't too high, like too small master voxel scale or too big master voxel scale, and you want to have the substeps so they're not ridiculously high and make the simulation slow, but they still have enough accuracy to get it working. So once you've seen the particles and done a scratch cache view of the particles, what you want to do is disk cache the particles onto your local computer, and then you should end up with a fairly small disk cache that will give you a really nice looking particle sim based off these particles that are here. So what you basically have is the particles need to be dense enough and need to be detailed enough that the mesh will be able to wrap tightly around them without having like any errors or difficulties or stuff like that. So you can see here the disk cache is set to the drive that I've already cached these particles to, and all you have to do to cache them is open up the scene, go to Bifrost, cache to disk, and it'll cache the file to disk in a fairly short space of time for the 200 frames that we're using it. And once you've done that, it'll automatically read in the disk cache, but you have to disable scratch caching and background processing. And why that is because the Bifrost will automatically background process and RAM cache the simulation without you sort of authorizing it to do that. So that's basically how to get the playback working with the disk cache, and just make sure to disable that scratch cache. So the next thing is we're going to go to a certain frame that has a lot of water sort of martini movement in it as it's being filled up, and we're going to use that frame as the frame to test how the meshing and the shader works. So probably somewhere in the middle is going to have an interesting kind of shape, and then with that frame selected, we're going to get enable meshing and put the right parameters on the mesh so that it's not too porridgey looking. So one of the problems with these liquid simulation software is you often have ultra detailed particle simulations, but very blobby looking meshes. And the reason for that is that the mesh actually generates this big kind of elastic pillow around all the particles. It doesn't actually just create a little dot around each particle and then sort of blends them together. What it does is it sort of envelops the whole simulation with a curvy triangulated mesh, and then that becomes this kind of sheet of water that that blends around the liquid. So here we can see this extremely dense mesh has got, you know, millions and millions of polygons in it, and the liquid on it actually looks quite smooth and not very sort of polygon, like boxy polygons. It doesn't look like a 90s 3D video game. It's got that really nice smooth watery look, and that's really critically important for rendering these liquids to look good. Even if it looks like, oh, that's not that detailed or haven't got the sharp tiny little, it'll still look really nice as long as it's a smooth meshed smooth looking surface, because when it renders, water actually needs those smooth flowing lines and surfaces to be able to work properly. So there's a couple of shaders in this scene: the Bifrost liquid, a Blinn, which is used to render the glass, which looks like martini alcohol, and a kind of milky liquid subsurface scattering shader. And we might also make a red wine or white wine shader later on that's really super basic. And with your shaders, the most important thing to do is get the color correct. A lot of people really overlook the simplicity of correct color. So if you're doing white wine, for example, if you have, if you have a reference image of white wine or milk or red wine or water, if you color pick the sample, the image, you'll find that the red or the amber color is actually quite different to how you initially imagined it would look. And what the objective of the exercise is to match the reference image to the CGI render that you're doing, so they just look the same as each other. And oftentimes you'll be able to achieve that just through using the color picker and getting the right RGB values on that shader's color and specular color settings. So it's a pretty straightforward process, and you don't need extremely complex materials to get it working. They just need to be the right color, because the human eye is very sensitive to colors, and you can easily tell the difference between red wine and blood and orange juice and all these different real life things that you look at all the time. So yeah, it's really important to have the right color. So this looks pretty good. We've just got the that simple shader on the glass, and the lights are set up in a way that they're bright enough to have the highlights on the glass visible, but they're not so bright that they make it look really artificial and fake. So if you want, you can increase the the lighting, but it really depends on what material you're putting on there. So for that milky material, the lights are too strong, whereas for the martini, they're a bit too weak. So you really have to adjust your lighting based on what shader and what setup you're using. So what we're going to have a try at now is making a duplicate of that Blinn shader to make a red wine material. So we've got 50% transparency and a kind of red, dark red color. And let's see how that looks when we render it. So we can see that this is, not too far off with the color, but the transparency is far too low, far too opaque. So it actually looks like a cup of blood instead of a cup of, you know, a cup of wine. So what we're going to do is change the red a little bit of a different color, and adjust the transparency, and see if we can get a more realistic looking shader. And these kind of tweaks and just experimentation and things like that is the best way to get the results that you want. So we can see here that even though the color is picked off a sample image that I opened earlier, it doesn't actually work because it's too brown and desaturated. So sometimes you have to really crank up the color and the saturation to be super high, and then you'll be able to get the shader working the way you want it. The other thing too is, in photography, something like wine might be like a really complex natural surface that is less transparent the more dense the wine is. But the trick is, you need to really, rather than setting up your shader like that, it's best to set it up so that you can get a realistic overall look rather than having the super complicated multi-high dynamic range subsurface scattered surface. You just need to get the overall look of the image matching somewhat to what you're working with. So hopefully that gives you a good rundown of how to do pouring liquids with animated emitters from scratch in Bifrost. I hope you enjoyed that class. If you have any questions, head over to the forums and post up your questions on there. Next week, I'm going to be having a look at doing a how to create like Hawaii 10-foot waves that are breaking over reefs, and we'll be setting that up from scratch as well. We're having a look at the influence of underwater collision geometry and how that affects the generation of waves. You should be expecting a pretty beefy computer to get this scene working. It's going to have a lot of particles and a lot of complex simulation happening, and hopefully it'll be really awesome, and it'll look really cool. So we'll be covering a lot of rendering, a lot of meshing. We're going to be going into the shaders and the ability to adjust the shader to get the look that you're looking for in the scene. And we've been also looking into how other renderers work with Bifrost at the moment, which I was working on this week for next week and the week after's class. But one thing to keep in mind is Krakatoa and V-Ray and RenderMan, the only versions of those you can get is for Maya 2014 at the moment, as opposed to many Maya 2015 or 2016, which is a lot of the sort of versions that are being used for this Bifrost course. So stay tuned, and we'll keep investigating the other renderers. But at the moment, it looks as though Mental Ray is the renderer that is currently available as of today, the 8th of 6th, 2014, to create Bifrost renders. But soon, I'm sure that there'll be V-Ray, Krakatoa, and RenderMan and Arnold rendering plugins available for Maya 2015 that will allow you to render out Bifrost at high detail and with more particle details and more detailed shaders. So stay tuned, and I'll speak to you guys soon.